here that we can play with some of these structures here in union and intersection. Well, what's really interesting about all of this is that that sets provide the basis for us to even be able to talk about things like addition and subtraction. Now remember, we have this whole idea of a cardinal number, okay? A cardinal number. And the cardinal number essentially answers the question of how many. And the whole numbers, set of whole numbers, is the set of all cardinal numbers. Okay, does this make sense? Okay, set of all cardinal numbers. Now in this case, the cardinal number for A, that is the number that is in A, is 3. And how do I do this? If you remember the process of counting, okay, I have a set of counting numbers, okay? 1, 2, 3, 4, 5, and 6, okay? And it doesn't stop there, it just keeps going on and on. But the process of counting starts with the set of counting numbers, and I match what is in set A in a one-to-one correspondence with a subset of the counting numbers. Now it has to be done in an orderly fashion. So it has to proceed with the first counting number and progressively larger. At this point where I stop, where I have finished all the elements that are in set A, this number right here tells me how many and is the cardinal number. Okay. On the other hand, if A is empty, there is nothing that I can match up in a one-to-one correspondence, and so we would say the cardinal number is 0. We do not start counting with 0. So you can see here that the process of counting this cardinal number. Okay. Now, in this situation, you can see that the number in A is 3, and that the number in set B is 2, and that the number in set A union B is 4. Okay. Now union is where we have put everything together again, but notice that right now this does not define what we understand as addition. How can we fix things up so that it would? Okay. Let's just take a look here at what's going on in this situation. Okay, because we can talk about a generalized counting principle for sets. Okay, and this idea of, it's also called the inclusion-exclusion rule. And if I want to talk about how many are in A union B, okay, then I can count all those that are in set A. And I can also count all those that are in set B. But you notice that what I have done here is I have done too much. I've counted this region twice. And since I can't count any region twice, I'm going to get rid of one of those, and I'm going to take out from that the number in A intersect B. This is called the Inclusion-Exclusion Principle. Okay? And what it demonstrates is that if you don't know whether sets, well, if you have sets that intersect, of course, it's going to affect what you have once you put everything together. For a definition of addition to work, I need to start off with disjoint sets. So I need to start off with disjoint sets. And so here's A, and here's B. And these two sets are disjoint. Okay. And so if I want to talk about A union B, okay, you can see I would be putting all of what is in A together with all of what is in B. And if I wanted to talk about the number in A union B, that would just simply be the number in A plus the number in B. Here, in this case, suppose I wanted to call the number in A to be a value, say, A, okay? And here I'm going to call the number in B to be the number in B. And you can say, call that little b. And you can see then that I am doing a little bit of what we understand as traditional addition. Here, this is the number in the union, so if we want to call this C, all right, that the number that's in that union C, C is equal to A plus B. Again, this refers to disjoint sets which have nothing in common. Now, these sets are going to have, this idea of addition is going to have some very, very basic properties to it, okay? And in fact, we alluded to some of these properties earlier, okay? First of all, if you're going to put sets together, all right, remember, if you're going to put disjoint sets together, you're going to get a set, okay? In fact, anytime you put any two sets together, you're going to have a set. And we know that every set possesses a property called the whole number, okay? And the whole number is essentially a description of how many, right? So if I am putting together two sets, two different sets, and that new set possesses a whole number, then I can talk about the fact that addition, every addition of whole numbers is going to produce a whole number. So every sum of whole numbers is a whole number. Okay. This property we call the closure property. It's one of the most basic and one of the least talked about, but probably because we understand it instinctively. You wouldn't expect to add two whole numbers and get something different. Okay. Well then, let's just take a look at this, and you can see that it really makes sense that A union B is the same as B union A, right? You can tell that it really doesn't matter if I take, well, let's see, here's elements star, square and triangle with element rectangle and circle, okay? And you can see that it really wouldn't matter if I took the elements here and put them into here, or if I took the elements here and put them into there. What would happen is I would have still all of the elements together. So it doesn't matter where I start, what I start with, and what I put into it, so long as the two sets get joined. And this is correct. So I can talk about the number in A union B being the same as the number in B union A. Well, that means then that A plus B is equal to B plus A for all whole numbers, all right? And I can call this idea that A plus B is equal to B plus A for all whole numbers the commutative property. Now, we call this the commutative property because as we visually look at the operation, you can see that A and B change places, and the operative root for this word is commute, okay, which essentially means to go from one place to the next. So here, this deals with a property of set. You can see how that works. A union B, B union A, you put it all together, and it doesn't matter. So here's the commutative property. This property is instinctive. You understand it, okay? So 5 plus 3 is equal to 3 plus 5, and that works. So this idea of addition right here. So we've got two properties now. We have got closure, and we have got the commutative property. Well, then there's another property here. Let's see what would happen, okay, if I added to A the empty set. Okay, so if I took A union the empty set. Well, we've already discussed this, and we have already said, well, that's just equal to set A. And that makes sense. Well, what are the cardinal numbers here? Well, the cardinal number here, okay, so again, what's the number in A? Okay, so is the number in A, so I know the number in A plus the number in the empty set is equal to the number in A, all right? Well, here's A plus something is equal to A. Now, obviously, this number right here cannot be one of the counting numbers, okay? Because if I, okay, the empty set, here's the empty set, okay? Here's the empty set right there, okay? And you can see it has no elements. We haven't even started counting yet because there's nothing there. So we have a unique number for this called 0. And 0 is the cardinal value of the cardinal number for the empty set. And so what is this? Well, we're going to call this the identity property. Identity property. And the reason why we're going to call it the identity property is because this is something where I am operating on A, I'm operating by addition on A, but I am not changing what A is. A remains the same. It has kept its identity. Does that make sense?